We are going to introduce thermal conduction in engineering mathematics. We will explore its introduction, physical mechanism, the Fourier series solution to the heat equation, and practical application examples. First of all is the introduction. Thermal introduction is the process by which heat is transferred from the hotter end of an object to the colder end. The ability of an object to conduct heat is known as its thermal conductivity, denoted by K. This process plays a crucial role in various engineering fields, especially in materials science and electronics design and application. We can categorize thermal conduction into several types. First, steady-state conduction. It occurs when the temperature difference driving the conduction remains constant over time. Second, transient conduction. It is a mode of thermal energy flow. It occurs when the temperature within the material changes over time. Third, relativistic conduction. It is a theoretical model compatible with the principles of special relativity, considering the finite speed of thermal signal propagation. Last, quantum conduction, a less common phenomenon where heat transfer occurs in a wave-like manner, similar to sound waves. This leads to a very high thermal conduction. Next, physical mechanism. The following formula is the thermal conduction equation. The physical mechanism of thermal conduction involves the transfer of kinetic energy between particles. When a part of a material is heated, its particles gain energy and vibrate more vigorously, subsequently transferring energy to adjacent, less energetic particles, creating a flow of heat. The process of thermal conduction can be described using Fourier's law of heat conduction, leading to the heat equation. About the graph in the right, the horizontal axis represents temperature along a metal bar. The vertical axis represents the temperature U, showing the temperature values at different spatial positions or time points. The graph shows temperature changes from hot to cool, moving towards equilibrium. U is the temperature distribution function, representing the temperature at a point x, y, z, and time t, and K is the thermal diffusivity of the material, a constant that characterizes how quickly heat diffuses through the material. The partial derivative of U with respect to time represents the rate of change of temperature with time. The second partial derivatives of U with respect to the spatial coordinates x, y, z represent how the temperature changes in space. The formula below states that the function U is equal to a constant K multiplied by the Laplacian of U. The Laplacian of U represents the divergence of the gradient of U, which in physical terms often relates to the flux of U. The Laplace operator can be written as the formula below, which combines the second partial derivatives of U with respect to three-dimensional space to measure the overall curvature of the function U.
And next, I will introduce Fourier series solution to the heat equation. And the slides explain the heat conduction equation module and its solution process. This partial differential equation describes the change in temperature over time and space. And U of xt represents the temperature at position x and time t. And K is the thermal conductivity coefficient. And next, the diagram illustrates a rod of length L. And we set the boundary conductions U of the 0 and t equals 0 is the temperature at the left end of the road is always 0. And U of L and T equals 0, the temperature at the right end of the road is always 0 too. And next is some conditions about the module. The initial conductions and x belongs to 0 to L, and U of x and 0 equals f of x. And the temperature distribution along the road at the initial time. And next, I will introduce the method of separation of variables to solve the equation. And use the separation of variables method to split the original equation like this. And this results into ordinary differential equations. And these slides collectively explain how to solve the heat conduction equation by setting appropriate boundary and initial conditions, and applying the separation of variables method to find a temperature distribution that satisfies these conditions. And at least, I will introduce the actual application examples of the heat conduction equation. The principles of thermal conduction have numerous real-world applications. Here are a few notable examples. One is the building engineering, designing thermal insulation materials based on their thermal conductivity to ensure energy efficiency in building. And the two is materials science. Understanding the thermal properties of materials helps in developing new alloys and composites with desired heat conduction characteristics. And three is electronic devices. Efficient heat dissipation in electronic components is crucial to prevent overheating and ensure reliability. And four is the materials processing. Control of heat flow is essential in processes like welding and additive manufacturing, where precise thermal management affects the quality of the final products. And for instance, consider a cubic metal material with a side length L. At the initial moment, the temperature distribution inside the cube is given as T of X, Y, Z, and T. We analyze how the distribution evolves over time under constant thermal conductivity and specified boundary conditions. And its problem statements. Like spatial range, the cube has side length L with x, y, z as the three spatial coordinates of the cube. And next is thermal conductivity. The thermal conductivity inside the medium is a constant alpha. And this is the boundary conditions. And using heat conduction equation, through the heat conduction equation, and incorporating all given conditions, this is an actual example of the equation's partial application. And thank you everyone for your listening.